So in this module, we're going to learn about randomness extractors, which are objects whose goal is to map random variables that have enough entropy into random variables that are as close as possible to being uniformly distributed. And we're going to discuss randomness extractors in the context of their application to privacy amplification. But I think it's worth mentioning that these objects have a completely independent life of their own. They were introduced in the field of pseudo-randomness in theoretical computer science, and there they found many connections aside from their application to cryptography, for example to the study of graph theory or to combinatorics. So it's really beautiful object. Let's see what they are. So what's an extractor? It's a function that I'll usually denote by x, which takes as input a random variable x about which we only have one piece of information, which is that the min entropy of this random variable x, conditioned on some side information e, could be classical, could be quantum, is at least k. So that's what's given about x, and our goal is that x produces a string z, which is such that the joint distribution of z and the side information e is uniform on z, so z will be here m-bit string, and this is the uniform distribution, so it's shorthand for totally mixed state on m bits, tensored with the side information e. So that's our goal, and we already saw in the context of privacy amplification that we're not going to be able to achieve this using a deterministic procedure, because if you take x to be a deterministic function, then it's always possible to set things up so that the side information e is very small, meaning that x has large min entropy conditioned on the side information, but still it is the case that this side information happens to contain just one important bit about z, so for instance the first bit of z. So in order to fool this kind of eavesdropper strategies, we have to use randomness. This extra randomness is going to be a second parameter that's provided to the extractor that we'll call the extractor's seed. So let's see the role of the seed. It's usually going to be called y, and this will be a random variable which will be distributed in 0, 1 to the d, so we'll have d bits of seed, and this seed will always be uniformly random. And then the extractor takes as input x, which is partially random, conditional on the side information, y, which is uniformly random, independent from the side information, and produces z, which now is defined as x of x and y. And now the condition will be that not only should the output be uniform from the point of view of the eavesdropper, but it should also appear uniform from the point of view of an eavesdropper who holds the initial side information e and also is given access to the seed y. So we'll put a y here to represent this seed. So this condition is the condition that's usually called strong extractor. It's strong because the eavesdropper also has access to the seed. But in this whole class, we'll only be talking about strong extractors, never the ones that don't have access to the seed and are called weak extractors. So sometimes we'll just say extractor, meaning strong extractor. So let's imagine that we have a strong seeded extractor. Let's see how this can be used in order to solve the task of privacy amplification that we introduced in the previous module. So if you remember this task, the setup was that there's a string x. This string x is communicated to both Alice and Bob, but Eve has some side information that can be correlated with x. And this is represented by a CQ state Rho xe. So that's exactly the setup for privacy amplification. It's also exactly the setup for randomness extraction. And in privacy amplification, the goal is for Alice and Bob to amplify this weak secret, coming up with a shared uniformly random string R. Here's how they can do it if they have access to an extractor. What Alice will do is that she'll generate a uniform seed in her lab, y, and here it's important that the seed is uniform and independent from the eavesdropper. So that's one assumption that we'll need for privacy amplification based on extractors, which is that Alice has a trusted random number generator in her lab, and that random number generator is independent from the eavesdropper's side information about the weak secret that she holds initially. So y should be uniform and independent of e. Then Alice will communicate y over the public channel to Bob, both Alice and Bob have the string y. They can compute the extractor by evaluating it on x and y. The result is a string z, which they're going to use as their output of the privacy amplification procedure. This is what we called RA and RB before. So in this way, we get a privacy amplification protocol which is always going to be correct. So it's correct with parameter 0, so 0 error in terms of the correctness. And now the security, well, the security for privacy amplification was that the trace distance between the joint state of the output, RA, and all the side information that's available to the eavesdropper, meaning the initial side information E plus the public communication, which here contains the seed Y, this should be close to a state that's uniformly distributed for the key or for the output of the procedure and tensor product with the side information. If you remember, this was the security requirement for privacy amplification, and this is going to be exactly the correctness requirement for the extractor, meaning that if our extractor is secure, then this protocol for privacy amplification. So we've reduced the task of constructing perfectly correct and epsilon secure privacy amplification protocols to the task of coming up with epsilon correct, strong seeded extractors. So before ending, let me give you a little bit formally what is the definition of a strong seeded extractor. So here we are, that's the formal definition. We have two inputs here, x and y. X is called the source, y is called the seed. So for the application to privacy amplification, x is the weak secret, and y is the seed, the randomness that Alice generated locally. And then we produce a m-bit string z, which we'll call the output of the procedure. And so we'll say that this function is a k, epsilon strong seeded extractor if it is the case that whenever x is such that the min entropy of x conditioned on side information E is at least k, then the output condition that the joint state of the output, z, the seed y, and the side information E, is indistinguishable from totally mixed state tensor product with the side information y and E. So this should be at most epsilon, and we'd like epsilon to be as small as possible. So that's a strong seeded extractor. So there's a lot of parameters to play with here. You have the n, which is the input length or the source length. You have d, which is the seed length. You have m, which is the output length. And then you have two more. You have k, which is the input or source entropy, and epsilon, which is called the error. And so the goal is to come up with constructions of extractors that sort of get the best parameters possible. So what do we wish in general? So the input length n is just going to be a given. That's the size of the weak secret that we start with. So we just think of it as some large parameter, but we have no control over it. Now k is a promise. It's a guarantee on the min entropy of this input. So we don't have any control on it either. It could be very small. You can think of it as we had in previous examples, linear in n. So k could be 1 minus p times n for some p which is a fixed number between 0 and 1. Say k is half n, for instance. That's a good setting of parameters to keep in mind. So if k is half n, this means that the amount of bits of uncertainty that are left in the source x conditioned on the side information E is about half the total number of bits. And so we'd like to come up with a procedure that extracts as many bits as possible, and so we want to maximize the output length m, and in this case we'd get an m, maximum m, which is about the uncertainty k. So our goal is to get to m's that are roughly as large as min entropy k, and we'd like to do this in the strongest sense possible, so with the smallest possible error parameter epsilon. And then for a given epsilon, which ideally would be exponentially small in the sort length, or at least in its min entropy, we want to have the smallest possible seed length. So why is this important? It's not too important, but the seed is something that has to be generated locally by Alice using her random number generator, and then it has to be communicated over to Bob. So in order to keep the protocol efficient, we'd like the seed to be small. What you can argue, however, is that the seed cannot be too small, In particular, it cannot be less than logarithmic in the source length n divided by epsilon. So if you want an epsilon to be exponentially small, so something like 2 to the minus n, let's say 2 to the minus 0.1 n, if we're not a little bit less ambitious, then the seed length has to be roughly 0.1 n, linear in n. So we're not really going to be able to beat this unless we settle for weaker errors, but then in cryptography, we typically want our error or security parameters to be exponentially small, so this means that we're going to have to focus on the case of longer seeds. And this is what we'll do in the examples that we're going to consider in the next modules.